Okay, let's go ahead and get started. Not too long a lecture today. A couple things I want to go through, and then I'm going to talk about the lab, which is lab 7. All right, let's go and get started. All right, so first off, before we dig into the lab for lab 7, we're going to talk a little bit about RS232 Serial. And maybe you've heard that term before, but RS232 is basically a standard for transmitting data over some sort of serial link. And generally that serial link uses some sort of asynchronous serial connection, meaning you have a start bit, you have a stop bit, you have data bits in the middle. But the standard itself, rather than just being how that works, it includes things about the electrical signal characteristics, what voltages, what are the current limits, what's the timing and capacitance of them, and so forth. And also a mechanical interface, meaning what does the connector look like, what are the pins on that connector, what are the signals that are available and what are the functions of those signals, and what are the endpoints, the two things that are being connected, what are those like. And this was a standard that was created a long time ago, 1962, and it was designed for kind of teletype computer systems and modems to connect from one system to another system in a remote location. So you might have one teletype connected over the phone lines to another teletype. You would type here, it would go across to the other end and come out there. Or it might be a computer system here, talks through a modem over the phone lines to another modem on the other end to another computer system or teletype on the other end. So it's been around for a long time. Now, the idea behind it is it was designed for point-to-point communications. And RS232 simply stands for, the RS stands for Recommended Standard 232. It's also sometimes called RS-232 or EIA 232, which is the Electrical Institute of America. But that's another standards group that has the same standard but under a different name. But the idea here is designed for point-to-point communications, meaning here's a system, here's another system, how do we get them to connect and communicate with each other? And specifically it was designed to connect a modem system to a computer system, or a modem to a teletype, which is kind of an older version of like a terminal on a computer system without a screen. It had a printer instead of a screen. Now, since it was designed for point-to-point systems, it defines two types of endpoints. One end is called the DTE, and one end is called the DCE. And what those stand for, DTE is data terminal equipment. That's the equivalent of like the computer or a terminal where you're typing stuff in. DCE is data communications equipment. That's the equivalent of like a modem or other thing that is actually communicating the data across like a telephone line or some other cable line or telecom line of some sort. So again, DTE, that's like the computer. DCE is the modem. And what RS232 is, it's the connection between those two types of pieces of equipment. So in other words, if we were to look at a picture of what that looks like, it's RS232 is right here between the computer and the modem. It doesn't have anything to do with the telephone line stuff going on here. It's just between the computer and the modem. So you would have one RS232 from the computer to the modem to send data to it. The modem would then send stuff across the telecom lines to another modem. And then the other modem would then send it over RS232 to the computer on the other end. So in that way, a computer could talk to another computer at a distance by using this modem. Now, the RS232 part is only this part right here between the computer and the modem. And you probably have like a cable modem in your house, or maybe you have DSL or something like that, a DSL modem. That's the same kind of concept. It's so the communication we're talking about is from the computer or terminal to the actual thing that does the router, or the whatever you want to think of that as, that actually does the communicating. Now, it was a wired system, so RS232 defines electrical signals. And notice that the electrical signals for output, a logic 0 is somewhere a voltage between plus 5 volts and plus 15 volts. A minus 5 output, minus 5 to minus 15 is logic 1. So in other words, it raises the voltage above 5 volts to output a logic 0, and it lowers it below 5 volts negative 5 volts to be a logic 1. So rather than like what we did in the lab, where it was just 0 volts or some voltage, 0 volts, 5 volts, 0 volts, 5 volts, this actually goes positive and negative. And there's a reason for that. The reason for that is if the line is disconnected, it doesn't show up as a logic value at all. Or if there's nothing on the line, it doesn't show up as a logic value at all. The other reason for this is that these higher voltages, a higher voltage differential like +5 to +15, allows you to drive signals over longer lines. Because remember, voltage is like electrical pressure. So the more pressure, the longer the line you can push the signal through. And also by having it be one goes positive, one goes negative, you're either flowing electrons one way through the wire or flowing them back the other way as you build up that either positive pressure or negative pressure. But that's why it's both positive and negative. Now, on the input side, it's the same voltage thresholds, but they lower the minimum voltage to +3 and -3. And you might think, well, why is this different than that? How would they ever communicate this different? But notice this allows it to have a wider range, and that allows for some voltage drop or some resistance on the wires themselves. In other words, you have to be compliant, you have to output at least 5 volts, but can go all the way up to 15 if you want to. But on the receiving end, you have to see at least 3 volts. So that allows you to have this 2 volts worth of drop, or even more. You could have up to 17 volts of drop if you put this there. So that allows you to have fairly long wires if necessary. Now, logic 0 that we see here, the positive voltages, that's called a space. Logic 1 is called mark in terms of that's actually old terms left over from Morse code, where they remember they had a paper tape and they had a thing that would scratch the paper tape or make a mark in it. Marks were when it was closed or there was voltage applied. Space is when it was open. So those terms, you'll still see those terms used today, mark and space, for that. Now, a couple things about the tolerance of the pins that are the electrical signals. It says that any signals can be shorted together without damaging it. They could also be shorted to ground without damaging it, and you can connect it to as much as 25 volts worth of electrical pressure, either in the positive direction or negative direction, without damaging the system. And what is it there? What is the electrical thing that's actually doing this encoding? Well, it turns out there's special driver chips that convert to and from those voltage levels. And a couple common ones that you might see used in designs are what's called the Max 232, made by a company called Maxim. But there are other drivers as well. If you go onto like the site we were looking at previously to look up the SPI chips, DigiKey, and you type RS232, there's just tons and tons of these driver chips that can both transmit and receive. But in other words, you just drop that chip in and you can output a 0 and a 1, a 0 and a 1, meaning 0 volts, 5 volts, and it will convert it to this positive and negative voltage range for us. The Max 232 is a nice chip because it only needs a single positive supply. Like, for example, you could have a single 5 volt supply to power that, and it will make the negative voltage using this technique called a charge pump. The Max 3232 is similar to the Max 232, except this allows a 3.3 volt input to produce the 5 volts with a charge pump, or the negative 5 volts with a charge pump. But anyway, if you're designing a circuit and you need to have an RS232 connection, there are tons of chips available to do that for us. We don't have to do any circuit design other than drop the chip in there and add whatever parts it says it needs. Usually a couple capacitors for the charge pump. All right, the physical connectors for RS232, there's several of those that are around. The most common ones are a DB9 on PCs. So on PCs, you'll see a DB9. Sometimes you'll have a DB25 on like a modem port. Sometimes on a PC as well. But those are usually male. And notice the pins I've kind of numbered here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this one has 25 pins. And that's what, if you look at those DB connectors, they're called that because the shape of this looks like a D. And the 9 is the number of pins, and the letter at the end, M, is that these are male. In other words, so there are pins sticking out of these that would then mate with a female connector when it plugs into the cable. So anyway, this is what the connector is like. There's also this RJ45, which looks a lot like an Ethernet connector. But there are uses of these for RS232 as well. There's some other ones as well. There's like a 10-pin version of this that I've seen. There's also a version of this that has a weird offset bottom on this, so it can't be plugged into the same thing, called an MMJ. But the most common connectors you'd see are DB9M, DB25M, and this RJ485 PC8 connector. It looks like a phone plug that you plug your phone, although most people don't plug phones in it anymore. But it looks like an old POTS phone line, little clear connector that plugs in. You've probably seen those on network switches and things like that. But though they're not RS232 on those. Those are Ethernet on those. It just has the same kind of connector. Okay, something about the physical characteristics of RS232. It doesn't really define the distances that you can use. And the reason for that is because it depends on the cable length that you're using, the type of cable you're using, the speed you're running it at. So the distance and speed and cable type are all kind of interlinked, so they didn't define any of that. You can, in practice, get over 1,000 feet. You can get much longer distances if you run the speed very slow. But one of the things, if you need longer distances than that, there's some other standards that are part of the RS set of standards that we're going to look at here in just a little bit, that are a little bit better for longer distances and higher speeds. RS232, though, is simple, and it's been around a long time. There's a lot of PCs and servers still have RS232 ports on the back. There's a lot of industrial equipment that still has RS232 ports on it. All right, the signals that are commonly used on those for RS232 on those connectors are, I've listed them here. So take a look at this table. This is the signal name using the mnemonic that's in the RS232 standard, a little description of that signal, like kind of a text description, the direction of it, meaning is it from the computer to the modem or from the modem to the computer, and then I included which pin it would be on the DB25 connector and which pin it would be on the DB9 connector. So in other words, the DCD, data carrier detect, that is from the modem, from the DCE device to the computer, to the DTE device. And it's on pin 8 on the DB25 and pin 1 on the DB9. And so if you look through the rest of these, DTR, data terminal ready, that is from the computer to the modem. Pin 20 on the DB25, pin 4 on the DB9. Now I'm not going to go and read all these. I'm just going to go through and read the ones over here. So DSR, data set ready, RI, ring indicator, RTS, request to send, CTS, clear to send, transmit data, receive data, signal ground, and the field or shield ground, or sometimes this is also called the kind of frame ground. Sometimes it's actually labeled FG instead of PG as well. But looking at all of these down through here, notice these signals, they're all conveying different information from one to the other. So let's take a look and dig down into that just a little bit to talk about some of those. So for example, DCD, data carrier detect. That is a DCE, data communications equipment, telling the computer that it's connected to a remote device. And if you remember back to what that picture looked like back here, that's the modem saying, hey, I'm connected and talking to somebody on the other end. I'm telling you that by raising that line, asserting that line, that I'm talking to that machine on the other end. DTR is the terminal device, the computer, saying that it's ready to communicate. DSR is the modem saying it's ready to communicate. So in other words, when they're powered down, those aren't asserted. When they power up and the program runs, they'd say, hey, I'm ready to communicate. I'm ready to communicate. And so there's some rules that are defined as well. For example, you're not supposed to send data to the DCE device if the DSR line says it's not ready. If the DSR is asserted, that means it's ready. We can talk to it. We should also not talk to it or expect it to send data across to the other end if it's not connected. So these are all telling us status information about the connection with that modem or that device, or about its readiness to communicate with a remote device. Request to send and clear to send, those are what are called handshaking lines. So RTS is the DTE, requesting clearance to send data to the DCE device. So it's basically saying, hey, I want to send stuff to you. And then if the modem is ready, it can then grant that clearance by asserting CTS and saying, you're all clear. You're ready, clear to send. There's also this RI, which is a ring indicator. If you remember back on the previous chart, that detects when the phone line rings. In other words, if it's a modem and it's not connected, the phone would ring, the RI pin would go, whoop, the phone's ringing, to let the computer know, hey, the phone's ringing, you should answer it. And then the ones that are most important, the ones that are actually sending the data, like you did in your asynchronous lab way back in lab 2 or whatever that was, TXD and RXD, those are, it's basically saying, or those are the lines that are actually sending the data from one end to the other end. But notice there are 2 of them. In other words, it's bidirectional. There's a way for the computer to talk to the modem and a way for the modem to talk back to the computer. So there's 2 data lines, one going from DTE to DCE, and the other one going from DCE back to DTE. And note that that full DB25 connector, we're only using a few lines back here on this previous page of that. That uses all of the ones on the DB9. On the DB9, the only difference is there's no difference in the shield and the signal ground. They're really the same connection. They're both ground. But on the DB25, there's actually a complete secondary data interface. It has TXD2, RXD2, request to send to, clear to send to, dataset ready to, DTR2, DCD2, and so forth. So it has a whole completely separate set. There are also synchronous communication lines that are defined for the DB25 standard connector, some of which are implemented and some of which are not, depending on the system. But note that these are the ones that are most likely that you'll encounter on the primary communication interface. All right, a quick picture here of what the connection looks like. And what I've done is I made a picture here that shows both ends. And these pins that I've labeled here, you'll notice that those are the pinouts for the DB9 connector. I didn't put the DB25 on there. So on the DB9 connector, I just labeled the pin numbers for convenience. But you'll notice that the ground doesn't really have a direction, but receive data, and notice I have the DTE on the left. This is the computer on the left, the DCE on the right. That's the modem on the right. You'll notice that it's a straight through cable. In other words, pin 5 goes to 5, pin 2 to 2, 3 to 3, 4 to 4. In other words, it's just a straight through cable. There's no cabling that changes in the middle partway through. In other words, 1 goes to 1, 2 goes to 2, 3 goes to 3, all the way up to 9 going to 9. But that means something kind of interesting. That means, for example, let's look at the transmit data line here. The transmit data line is an output on a DTE device, because that's how it's transmitting data. But the line labeled transmit data on a DCE device is an input. It's a receiver. So where does a DCE device receive its data? On the transmit data line. It's a little counterintuitive when you first encounter that. But there's an easy way to think about that, and that is that it's always labeled from the point of view of the terminal device. So every line is labeled from the point of view of a DTE device. So in other words, transmit data, that is from the point of view of the terminal. So if I'm not a terminal, if I'm a modem, then the transmit data is where it's transmitting data to me. The receive data is where I send data to it if I'm a DCE device. Now that can be confusing. For example, if you're wiring up a wireless module that supports something like RS232 or even just a UART, and there's a TXD and an RXD, you have to know, is that from the point of view of the module transmitting data, or is it from the point of view of it talking to another host and receiving the data that's transmitted to it? So you got to look, and the way to know that is a lot of times the documentation will say it's set up as a DCE, and they should say DTE to DCE. Let me fix that real quick. It's a typo. Okay. So In other words, it depends on if it's a DTE or DCE. But if you have one of each, it's a straight through connection. There's also a ways to connect these where you don't necessarily need all of these extra status lines. You could leave some of that. Like, for example, if you're connecting something and you don't care that the phone rings, you can leave that wire out. If you don't care about handshaking and requesting and being cleared, you could leave those out. So there's a minimum wire connection version of that to communicate between two different systems. And it would look something like this. Now, DTR, DCD, DSR, RTS, CTS, we would have to have a program that doesn't care about those or doesn't use those handshaking and status lines. But you can have two machines communicate with just these three lines. You need the ground, you need receive data, you would need transmit data. And if it was only a one-directional communication, like you're only sending data, you could get rid of the receive data as well. Now, there are also some non-standard uses for this, and that is connecting a DTE to a DTE. But to do that, we would need a special cable. So to do that, here's a DTE connecting to a DTE, and we would need to say, since it can't be a straight through cable, because just like talking on the phone, you can't talk into the ear part and listen on the mouth part. You need to have those switch when you're talking on it. Can't hold the phone upside down. It doesn't work that way. One's a speaker, one's a microphone. If you flip it upside down, it's not going to work. So the same thing is true for connecting a DTE to a DTE. So in other words, this is a computer connected directly to another computer over a serial connection. And we can use those serial ports, but we need to use this special cable. And those cables have a name. They're called a null modem cable, and null means none. So this is like a cable when you're using no modem. It is not a no modem cable, so don't go talking to somebody and saying, hey, I need a no modem cable. It's a null, N-U-L-L modem cable. And what a null modem cable does is it crosses over the lines as needed. And if you look at how this crosses over, you'll notice that transmit goes to receive, and receive comes from transmit. So in other words, we've switched the two ends so that the transmit goes to something that's listening, and we're listening for something that transmits. But not only that, there's some other connections here as well. The DTR, the data terminal ready, goes to the data carrier detect and data set ready of the other one. In other words, when we assert that we're ready, that tells them that we're ready. And notice the data carrier detect is part of that, because we're also saying, and we're connected to somebody on the other end. So we're saying, hey, the guy on the other end is ready, and he's connected. And so you notice that configuration, the last one that gets crossed over, is request to send goes to clear to send. So when we say we're ready to send, it tells them we're clear to send, and vice versa. So this is a standard null modem. And notice the ring indicator is left out, because there's not going to be a telephone that rings, because we're connected directly to that other end already. And we don't have to worry about the phone ringing, because data carrier detect says we're connected to somebody. So the phone is never going to ring, but we're already connected to somebody on the other end. Now there is a minimum wire configuration of this null modem cable that cuts down on the number of wires for this as well. So rather than needing, if you count the number of wires, we have 1, 2, 3, 4, 5, 6, we have 7 going through here. We can cut down on the number of wires by doing this kind of little trick like this. And this is kind of a minimum null modem cable configuration that, again, we just have 3 wires. We have ground, receive, and transmit. But what we've done is we've looped these back. So when we say we're ready, we tell ourselves that the other end is ready and connected. And when we request to send, we also clear to send ourselves. So we're saying, hey, we're ready. Oh, somebody, it's like getting our echo back saying, we're ready. Are we ready? Are they ready? Yes, they are. And so this is you'll see cables that are wired like this for a minimum, much fewer wires needed for longer distances or whatever to get a computer to talk to another computer. Now, you don't see serial ports a lot in computers anymore, but they are in things like servers, even uninterruptible power supplies. UPSs have serial ports in them so they can talk to a server. So you'll still see these kinds of things, ports on devices. And a lot of times they'll use something like a null modem cable to talk to each other. And we're going to talk about some other things here in just a second. Now, related standards that are similar to RS232 but came a little bit later and offer advantages. There's a thing called RS422. And that's similar to RS232, but it uses what's called differential signaling. And what differential signaling is it means that every line, rather than just having a receive and a transmit, the receive has two lines, two wires, and the transmit has two wires. Now, what's the advantage of that? Because it seems like we're just adding extra wires. The advantage is that you can actually have much longer distances, because what happens on those two wires, it's differential, meaning that one goes low, one goes high, and then to send logic 0, and then to switch, they flip, and one goes high, the other one goes low. And so you can get distances that are much longer and much higher speeds. RS422 can also have one driver chip, one driver output drive or communicate with up to 10 receivers that are listening to that. And some drivers can actually support more than 10 receivers, but the standard itself says one driver has to have at least 10 receivers it can talk to. And what it has is these two lines that are they're labeled A and B, and essentially that's like a plus and a minus. And you can see that here. And the idea is if A is above B, then it's as logic 0 or a low. And if B is above A, then it's a logic 1 or a mark. So in other words, having the signals this way means one logic interpretation. Having them this way, the opposite, means the other interpretation. And as long as there's at least 0.2 of a volt or 200 millivolts between the A and the B, it can receive that. And so that's why you can drive this much longer distances, is because it can start out with a very high voltage difference, and by the other end it can be very low. And then since you're switching them, you're actively pulling one high, pushing the other one low. You can get much longer distances out of it at much higher speeds. Now, there's another standard, and this one is probably the most used for things that you would encounter on a regular basis, other than RS232, which is around for legacy reasons. But RS485 is used all over the place, and I'll talk about a few of those examples here in a second. But it's similar to RS422, but instead of having a transmit plus, transmit minus, receive plus, receive minus, it actually has allows true multi-drop communication, meaning you can have just two wires, and on those two wires, you can have one system send out a message, the other to another node on that network, and another one then respond to that message. So it allows multiple nodes to kind of share just two wires. And it's still differential, just like RS422, but you can have a whole bunch of nodes listening, one of them take over the line and communicate, and then let go of the line again and go back to listening. And this allows multiple nodes. The standard allows at least 32, but in practice, depending on the number of what they call load units that are defined for particular devices that are listening, you can have up to thousands of things sharing those lines. You can still get up to 5,000 feet out of it. Each signal, or really there are only two signals, which are a non-inverting signal A, sometimes called D+, or the inverting signal B, sometimes called D-. And again, they're just this way or that way. They switch. And notice, because they are differential, we don't even need a ground. So you can have this RS485 network that just has two wires that connect to thousands of devices and have them all be able to communicate with each other. An example of what that looks like, here are the two wires. Notice there's no ground, because all that matters is how far apart they are voltage-wise. So when they're idle, you'll notice that the D+ line idles slightly above D- by a little bit. And you'll notice what happens is then when D- goes above D+, that's essentially a logic 0. And when they switch and D+ is above D-, that's a logic 1. So this is what A would look like, capital A. So 0, 1, 0, 0, 0, 0, 0, 1, and the stop bit. And the stop bit will always be the opposite of the start bit. So in other words, this is kind of what we saw with, if you just follow the D+ line, it looks a lot like what we did with our asynchronous communications previously. But you'll notice that there's also a D- line that just runs opposite of that. And that means we don't need a ground. that means we can get much higher distances out of these and at much faster rates, because it's always one goes high, one goes low. And usually these are wired with what's called twisted pair wiring, which is what's inside of an Ethernet cable, if you're used to seeing those. And because of that twisted pair nature of those wires, where they're kind of in a spiral, that makes them very immune to noise causing effects on this. And the reason for that is any induced noise would affect both of the wires in the same way. So you get I don't know, a machine turns on and makes a spike, both of these would jump up. But since it's differential, all that matters is the distance between them. It's unlikely one will get affected and the other one won't. And the twisted pair nature of that means that they're being affected in the same way by some noise source. So you can run these in very noisy environments over very long distances at pretty high rates and not have them be affected by external noise very much. They're very reliable. Now, that leads them to be used in multi-drop networks. Like you see here, here's a bunch of devices all sharing the same, just 2 wires. And any device could talk to any other device as long as it has some protocol to use. One thing that's important on RS485 networks is this terminating resistor. And the reason for that is when these get taken over and stuff gets put on there, you don't want things hanging out that make them act like an antenna. And you also don't want the signal kind of hitting the end of the wire and then kind of bouncing and back and forth. So they have what's called a terminating resistor that's usually put at the 2 end nodes on the thing. Those are usually like 120 ohm resistor. And essentially what that does is any signal that's put on there has a little bit of damping to it. So you don't end up with a ringing behavior on where it's acting like its own oscillator with the signal bouncing back and forth on here. But because they are reliable and only need 2 wires, you can have any number of nodes, thousands of nodes if necessary. That makes them a popular choice for industrial networks. They're reliable, they're easy to wire, very few wires, they can communicate at high speed with a lot of nodes sharing that connection. Now, because they are used in a lot of applications, a few of those I listed here that I know of that they're used in. Aircraft cabins. When you're sitting in an aircraft and you push the little button that says you want service, or the little light turns on and goes bing, fasten your seatbelts, there's a vehicle bus that's communicating that information that tells those lights to turn on, or when you press the button, it sends a message to where the flight attendant sits so they can see that you need help. How does that communication happen? RS485. It looks a lot like a network like this. Just 2 wires that run through the entire aircraft cabin. It's a very low speed communication, but very reliable. No noise affects it. So they call it the aircraft cabin vehicle bus. But there's also factory and automation versions of that. There's a thing called Modbus, Profi Bus. Those are used for factory automation. There's Alan Bradley makes a version of logic controllers that are used for, those of you who are in the CET degree might know what I'm talking about. But programmable logic controllers are essentially like a little computer inside of a device, and you program using this thing called ladder logic to get them. But the way they communicate with each other and with other devices is using this DH485, which is really just RS485 with a protocol sitting on top of it. Also, you guys have seen RS485 in action. I can guarantee it. If you've ever been to a rock concert or a show, and the colored lights change and the lights sweep, and they or the colors change and the lights come up and they point upward and they point toward the crowd, and then fog machines turn on. The way that all of that stuff communicates is using a communication protocol called DMX 512, which is a kind of a show control protocol. But really, that protocol sits on top of, as its communication system, RS485. So if you can talk in RS485, you could talk to those show control systems and send out the messages to say, set the light color of this light to this, change the position of this thing to this, sweep this one over that way. And there's entire software that drives those kind of concert performances, usually with somebody controlling those things. Dimming values too. Dim this light to half, pointed in this direction. All of that is RS485 that drives that. There's also Digital audio, if you have a digital audio like connector on the back of your high-end stereo equipment or synthesizer or sampler or whatever, and it's an AES3, that's actually RS485 that's communicating digital audio information between the devices. Also, a lot of security networks like fire alarms, smoke detectors, security camera interfaces for motion detecting and stuff like that. Those use RS485 as well. There's just tons of places it's used. And the reason for that, very simple, very small number of wires, but even though it's simple and has a small number of wires, very reliable and very easy to implement. Okay, so that's it with the lecture part of what I was going to cover today. Now I want to talk about the lab. And the lab doesn't have anything to do with RS232 or RS485. The lab itself, what we're going to do is you're going to do some self-clocking code programming. And let's quickly review what we're going to do. Well, it says let's take a look at the lab sheet. We'll come back to that later. Let's review self-clocking codes, and then we'll come back to the lab sheet here in just a little bit. So self-clocking codes, the idea was we want to combine the clock and the data into just one signal. In other words, we have one channel, one signal, but we want both the clock and data to be combined on that. There are a lot of ways to do that. The ones that we had looked at that we're going to review are pulse distance encoding. Pulse distance encoding, it looks at the ratio of the high part of a pulse to the low part. It could be inverted or use different ratios than we show here, but the idea here is if we have short pulse, that's a logic 0. Short pulse, long pulse is a logic 1. So in other words, it's pairs of pulses that matter, not something like just timing off a thing like we did with asynchronous communication. So in this case, this pair is a 0, this pair is a 1, a 0, a 0, and so forth. Now, there's also pulse length encoding, which all that matters is the length of the pulse at the top of this. So we don't care about how long it's low. We just say that's a 0 because that's a short pulse. This is a long pulse. And with that, we would need to have some reference length to know what counts as short and what counts as long. And sometimes that is established by having a preamble period. In other words, the message would always start with a certain length, and then everything that would be used as the yardstick for all of the subsequent bit widths. And one such system that we looked at previously that uses that pulse distance encoding, not pulse length encoding, but pulse distance, is this infrared remote controls, the light that comes out of here, the way that's modulated. 0 is short, a 1 is short, long. So you can see that here, that both logic 0 and logic 1 have this 562 microsecond high pulse, but then a logic 0 has a ratio of 1, also a 562 microsecond low pulse, but a logic 1 it's a 1 to 3 ratio. 1, 562, followed by 1.6875 millisecond low, or 1,687 microsecond low. And there's also what's called the sync pulse at the beginning that tells it, hey, there's a message that's about to be coming. It's 9 milliseconds followed by 4.5, but then after that, you'll notice that, so it's like a long pulse followed by half of that. So that's a different ratio than the rest of these, and it also can set the timing for how the rest of this is going to look. Okay, another one that we looked at previously is called Manchester encoding, and what that does, and this is used everywhere as well for a lot of different communication systems. Ethernet uses this. Infrared remotes also some of them use a version of this. RFID, like RFID tags that are in things, use this. Wireless networks, satellites, radio frequency stuff, space probes, hard drive platters. And Manchester encoding is so widely used because A, it's really simple, and B, it does a 0 bit has the same length as a 1 bit. Like, for example, back here, notice that 1s took more time. 0s took less time. This has the advantage of a 0 and a 1 take the same amount of time. Now the advantage of this is both zeros and ones have a transition right in the middle of them. A 0 goes from high to low, a 1 goes from low to high. But they look like that, so you just stick those together to make the message you want to send. There is a problem though. How do we determine where this first one starts? We always stick a preamble bit on the beginning, and we covered this two lectures ago, so if you want a more detailed explanation of this, go back and look at what that be, lecture 9. But we stick the preamble bit on the beginning, which acts kind of like our start bit that allows us to see that first transaction, and then from that point we know that was always a 1, so now we can see what the rest of the transitions were. And it's easy to do that using this kind of algorithm like this. And this algorithm basically says that the next bit is going to be, after this we see that transition. If it's a long period that's high, we know that's a logic 0, and we're at the middle of that 0. If it's a short pulse that's high, we know the next bit is a logic 1, and we're at the beginning of that, so we need to move ahead to this middle to then count off the next one. So the idea here, sending is really easy. We delay the line, or we set the line high, delay, set the line low, delay. Or for a logic 1, we set the line low, delay, set the line high, delay. So sending is very easy. Receiving is a little more difficult in that it depends on what the previous bit was, what happens. And what we came up with in lecture 9 was kind of this state machine. So in other words, we're in idle. We measure, or we have that falling edge and measured the t time to get us to the middle of that first bit, the preamble bit. And then from there, it's just a state machine. If we have a short pulse that's high, we have a logic 1. We get a short pulse that's low, we output that one. So this gets us to the start of the 1, this gets us to the middle of that 1. And notice we're always outputting it when we reach the middle of that. So then if I have a long output high, I go to the middle of 0 and I output a 0. So it's always going into these two that I'm actually performing an output. And so every 8 bits we output of this, transitioning back and forth, we output a data byte. There's no need to resync between bytes. We can actually run as many bytes as we want together because we're always using those transitions to determine. And that's why this is like a self-clocking code. We could be recomputing t dynamically, our time constant by which we're determining what's long and what's short, kind of averaging those as we get them. But the idea here is pretty simple. Okay, now that we've reviewed that, let's take a quick look at the assignment sheet. So let me pull that up. All right, so looking at the assignment sheet here, I suppose I should switch it over so you can see what I'm looking at. So looking at this assignment sheet, you'll notice a couple things. First thing, it says that for this lab, you're just going to use 2 Arduinos, simple wires to connect them. And there are 2 parts to this. Part 1, you're going to implement a system using pulse distance encoding, which is that one where it's a pulse, the pulse ratio that matters, the high part to the low part. And then part 2, you're going to implement using Manchester encoding. So pulse distance encoding, I have the description here, but the basic idea is, again, you're going to send 8 bits of a character, 1 bit at a time, and a logic 0 is 1t low followed by 1t high. I'm doing the opposite of what was in the lecture here, rather than 1t high followed by 1t low. The reason for that is that allows the line to idle high like it did in your previous lab. To send a 1, it's going to be 1t low followed by 3t high. And then once the message is complete, just send a low pulse of 3t at the end. But the idea here is that on the receiver, you're going to be looking at that. You're going to measure the amount it was low. You're going to measure the amount it was high. You're going to compute the ratio. And if the ratio is closer to 1, then it's a logic 0. If the ratio is closer to 3, then you're going to report a logic 1. And once you have 8 bits, print out the message you received, and then go back to waiting for the next low pulse. If the low pulse is ever closer to 3t than 1t, then you are going to reset back to the beginning again and wait for the next message. Now, One of the things about this, the cool thing about this is you'll notice that in the receiver, it doesn't have a predetermined time t. It's just measuring the ratio of those. So that would mean on your transmitter, to demonstrate this to yourself or implement this working at 100 millisecond and 10 millisecond time for t, you only have to change the transmitter. The receiver should just work. And this is actually, again, because it's a self-clocking code. All it cares about is the ratio, not timing off anything blindly like with the previous one. Now the second program is doing the same thing, but using Manchester encoding. And for Manchester encoding, go back and look at the lecture, but I give you a description here that a logic 1 is a 1T low followed by 1T high. A 0 is 1T high followed by 1T low. You're just going to output those. The transmitter for Manchester encoding is really simple. Receiver is a little more complex. On the receiver side, you're going to need to have like that state machine, kind of like we had, and determine whether is it a long pulse, is it a short pulse. If it's a long pulse, then you end up in this part of the state machine, and when we transition, we output that. So what I would suggest you do on that, when you get to that part, go back and look at this state machine and try to follow that. Now you can do it with a bunch of if statements, or you could do it with a state machine like with a switch case. So for example, switch state, and then have this be state 0, this state 1, that state 2, that state 3, that state 4, and so forth, and have it jump from one state. And what I would do is, rather than calling them 0, 1, 2, 3, 4, I would do a pound define, say pound define state idle as 0, pound define state 1 as mid 1, pound define start 1 as 2, and so forth. You could also use an enumerated type, if you remember that from C, using an enum. You could define an enum, make a set that has the idle, mid 1, start 1, mid 0, start 0 in that enum, and then use those throughout your code, just as a little hint there. Okay, so essentially you're going to do that. That's it for what you need to do. So you'll get it working with Manchester encoding. And again, with Manchester encoding, since it's a self-clocking code, you should not, after you have the receiver implemented, you should not need to change it to change the number of bits per second. You can do 1,000 bits per second or 10 bits per second by only changing the transmitter, because that's the only part that has this time period t defined, because this is using just the amounts of time. And is it a long pulse or a short pulse to determine the next thing to go. So that's it. So I'm going to give you the rest of the time today to work on that. And you really should be able to at least get one of those working by the end of class today. This pulse distance encoding is pretty easy. This one, Manchester encoding, the transmitter is really, you can get that typed up in 10 minutes. The receiver might take a little more effort, but again, when you go to work on that, if I were you, I would go back and look at this. Or you could look at this, but I would look at that and try to follow how that works, because that's going to be your best bet to getting this thing working. Okay, so going back to the presentation, that's it. We reviewed self-clocking codes a little bit. We looked at the assignment sheet. A note for this lab, though, that you are going to be submitting 4 programs, 2 for part 1, a transmitter and receiver for part 1, a transmitter and receiver for part 2. So make sure when you save these or work on them, don't do it accidentally save over the top of the previous one. And to submit those, just make a zip file and call them something like Lab 7 Part 1, Lab 7 Part 2, or you could say Lab 7A, Lab 7B, something like that to keep them straight, and then put them all in a zip file and submit that whole zip file. And that's it for today. Work on those labs or the previous one. If you don't have the wireless lab working, work on that. It's going to be a little bit before we have our next lab. I'm going to give you some time to work on those ones that we have, so I'm not going to start overloading you with more labs. So don't worry too much about that. There are some other things I'm going to cover in lecture, but it's going to be a little bit before we have once we get into the networking part of the class before we have more labs. So work on those, try to get those working. And other than that, stay safe. If you have questions or get stuck, let me know. I'm happy to help. And we'll see what we can do. See you next time.